Hello everyone. Today we are going to derive the expression for natural frequency of a single degree of freedom spring mass system. There you could see the spring mass system. It is an undamped system. There is no damper that you can see there. Okay, so first let me define the stiffness of the spring. As you could see that the stiffness of the spring is denoted by the notation K. Conventionally, and you could also see that there is no damper. It's always a good habit to remember that the stiffness is actually a property of material as well as it is a property of geometry. It is a property of material, what material this entire system is actually made of. And it is also depending on the geometry. So stiffness is both a property of material and geometry. So we are going to do a little bit of Gedanken experiment now. That is, Gedanken is a German, I'm not sure if I'm pronouncing that correctly, but Gedanken is a German word for thought. So what we are going to do a little thought experiment, that is, just imagine that you are stretching this mass by an amount x, okay? Alternatively, you can also compress the mass by an amount x, but for now we will assume that you have stretched this mass by an amount x. So the maximum stretching, it would be good if you represent that by capital X, but I'm trying to derive a very generic equation. Okay. Now, this mass, when you stretch by an amount X, the moment you leave this mass, the spring is actually going to pull this mass back to its equilibrium position. So there is an action force that is actually pulling this mass back to its equilibrium position. So let me represent the action force, which is the spring force that is actually pulling the mass back to its equilibrium position. So how do you write that? We know that stiffness is the amount of force that is required to stretch a spring by a certain distance. Say, for example, in our case, it is x. For example, if the stiffness of the spring is 1000 Newton per mm, the physical meaning is you have to apply 1000 Newton magnitude of force in a specific force in order to stretch the spring by 1 mm. So that is the physical meaning of 1000 Newton per mm. Okay. Now we can work for the action force. Action force F action is equal to K into X. So that is the action force that is actually pulling the spring back to, that is actually pulling the mass back to its equilibrium position. We know that according to Newton's third law, for every action, there is going to be an equal and opposite reaction. So let me write the expression for reaction here. You know that what is going to offer the reaction? In our case, it's an undamped system. So damper is not going to contribute to the reaction. So the one thing that is actually going to offer the reaction is going to be the inertia of the mass. So the reaction is given by the Newton's third law, so that is denoted by R. It is simply mass into acceleration. We know that X is the expression for displacement and dx by dt, or x dot, that is the expression for velocity. So we know that the expression for acceleration is d square x by dt square. So that is the expression for acceleration. Mathematics is just like moving objects. What we are going to do is we are going to take this acceleration and we are just going to substitute here. So when you do that, the expression for a reaction now becomes reaction is equal to m into d square x divided by dt square. So that is the expression for reaction. So action should be equal to the negative of reaction because both the forces are in the opposite direction. So we will equate them. So we get action, which is kx, is equal to negative of the reaction, which is m into d square x by dt square. I can bring this right-hand side term to the left-hand side. So the negative becomes positive. So I'll be getting m into d square x by dt square plus kx is equal to 0. What I'm going to do now is divide by k on both sides. So I'll be getting d square x by dt square plus k divided by m into x is equal to 0. Just dividing on both sides, left hand side and the right hand side by m, I'm getting a governing differential equation. Okay. Now let us keep this as star equation number 1. Okay. I'm going to come up with one more equation. That is, imagine the same spring mass system, but one difference, there is a slot that I have cut here. Okay. Now we could see the slot here. It's the same mass. Okay. It is the same mass. There is no difference in the mass. The spring also has the same stiffness K. Absolutely no difference. It is also the same spring mass system. Okay. So what we are going to do is, when you stretch it and leave it, the mass is going to oscillate to and fro, up and down. It's just going to oscillate up and down, like that, right? So when the mass is oscillating up and down, that's quite intuitive. You come up with your mechanism. That is, you construct a mechanism. It's an imaginary mechanism. It's a fictitious mechanism. There you could see the link there, okay? And it is perfectly frictionless system, which means that when the mass moves up and down, the link is just going to, the tip of the link is just going to follow a circle, which means that it's a mechanism. It's a mechanism that actually converts the reciprocating moment into rotary moment. Okay. Okay, that you can see. You just have to imagine that when this mass is moving up and down, so what happens is the link, let us say that it starts to rotate like this. The link starts to rotate. It maybe initially it's perfectly in the equilibrium position, perfectly horizontal. The mass is here. This is the initial position of the mass. And as the link starts rotating, which means as the mass starts moving up, the link starts rotating this way. Okay, as the mass starts moving up, then it continues to move up, and it reaches its maximum position here. So that's the maximum position. Then it comes back, and comes back to equilibrium position. And it also stretches the spring on the other side and reaches a maximum position on the other direction. Okay, so that's it. So that you could see how the mechanism actually works. So as the mass moves, what happens to the link that is initially horizontal? So let me represent the equilibrium position of the link. So this is the equilibrium position of the link, 0 degrees. Okay. And as the mass moves upwards, the link starts rotating. It starts, say for example, now it has rotated by 45 degrees. Okay. Which means that what is the distance the mass would have moved? Well, the mass would have moved up to this distance. So let me represent the distance moved by the mass. The mass would have moved up to this distance. Okay. There you could see the vertical component of this link. Okay. So that is the distance the mass has moved. Okay. So which means that the distance the mass has moved can now be represented by x. Of course, it changes with respect to time. So that is the distance the mass has moved along the vertically upward direction. Okay. The mass continues to move and it reaches its maximum here. All right, fine. Let us say that the maximum distance the mass moves is when the link reaches this position, which means the maximum distance should be equal to the length of the link. The length of the link is capital X. So that is the maximum displacement of the mass. So X max. Okay. Now we could see a triangle. So let me give the notation for this triangle. So maybe I could call this as A. Let me call this as B. Let me call this as C. Now we could see the angle theta. Of course, theta is a function of time. Now we can come up with an expression for theta now. That is, you see, velocity is distance divided by time. Angular velocity, omega, is angular distance divided by time. So this gives us the expression for theta, which is omega into t. Okay, so that's the expression for theta. Now let us find what is sine theta. So what is sine theta? It is opposite side, which is x of t, divided by hypotenuse side, which is the link distance, x. So this gives us the expression x of t is equal to capital X into sine theta. In the next step, I can write x of t is equal to capital X into sine theta is omega into t. Getting the expression from here, it is omega into t. Okay, that's the expression for displacement. Now, I can differentiate this expression two times. I can differentiate this expression one time to get the expression for velocity. So I'll be getting capital X into cos omega t. And if you differentiate omega t, you get omega. So that can be pulled outside. I can write it as omega here. And in the next step, I can differentiate this one more time to get the expression for acceleration. So acceleration is d squared x by dt squared. That is equal to capital X into differentiation of cos is minus sine omega t. And if you differentiate omega t, again you get omega. So outside already you have omega. So omega into omega is omega squared. In the next step, you could see that what is this term? This term that you see is the same as this term. Okay, so that enables me to substitute for capital X sine omega t. So I'll be getting in the next step d square x by dt square is equal to minus omega square into x. Okay, so substituting for capital X sine omega t as omega square into x. Okay, fine. In the next step, I can just bring this equation, the right hand side term to the left hand side. I'll be getting d square x by dt square plus omega square into x is equal to 0. So that's again a differential equation. So I got two differential equations. One is the differential equation that I got for this particular, both are the same systems, okay, for this system. And the second one is the differential equation I got for the same system, except that I have considered a mechanism. Just keep it in mind that this mechanism is a fictitious mechanism. It's an imaginary mechanism, and there is absolutely no friction. Okay, it's in our imagination. If there is a friction, then of course you know that it's going to dissipate energy and the damping will die down. Because there is no friction, if you just plot this as a graph, if you see that if you plot this as a graph, then if you plot the displacement along the y-axis and the time along the x-axis, you could see that the displacement varies in a sinusoidal manner with respect to time. Okay. Now we have got two differential equations. Maybe the first star equation number 1, maybe I can call this as star equation number 2. Okay. Now if you look at these two differential equations that we have derived, maybe I can bring this differential equation over here. That I can bring it here. So let me bring this differentiation equation, maybe the star equation 1, so that I can compare them. And if you look at the two equations, star equation 1 and star equation number 2, you could see that d squared x by dt square is there on the left side. It is also there on the right side on star equation number 2. And you could also see that the letter x here, it is also here and it is also here. But in place of k by m, there is omega squared term there. So I can say omega square is equal to k by m just by comparing. So I can say omega is equal to root over k divided by m. Of course, it's in radians per second. So that's the expression for natural frequency in radians per second, because you could say that if you want to convert this into cycles per second, that's perfectly fine, because you could say, for example, 2 pi radians will be 1 cycle. So how much radians, omega radians would be how many cycles? Okay, and that would be omega divided by 2 pi cycles. Of course, this is omega radians per second, so omega by 2 pi cycles will be for 1 second. And this gives us the expression, a more general expression for natural frequency. Fn is equal to omega by 2 pi, omega n by 2 pi to be very precise, because this is natural frequency. So we can always, it's a good habit to add the suffix n here because it is the natural frequency. We will always add the suffix n. Okay, fine. This is the expression for natural frequency. Okay, you can say it's 1 by 2 pi, substituting the value for omega n, which is root of k by m. So that's the expression for natural frequency. Okay. And one more thing that we have to keep in mind, that is, you could say that this is the expression for natural frequency in cycles per second, and you can also call this as hertz. Why it is a natural frequency? Because you could see that in this imaginary mechanism, if you just plot it as a sine curve, when this mechanism and this link, when it is perfectly horizontal, it's going to be 0. Okay, it's going to be 0. So let me represent that even more clearly. Okay, so you could see that it's 0. Then when the link increases, rotates, the magnitude of displacement increases in a sinusoidal manner. So that is x. When it reaches the maximum, it reaches the maximum. When it reaches the maximum, it reaches this position. When it comes to this side, okay, of course, it comes like this. Okay, it reaches the equilibrium position again. When it rotates again on the other side, it increases. And when it reaches the maximum, of course, it also reaches the maximum on the other side. When it comes back to the equilibrium position, that is one cycle that you could say that this is one cycle, which means that the mass would have moved from here. It reaches the compression on the other side. It comes back to the equilibrium position, comes back to the extreme position on the other side, comes back to the equilibrium position. So that is one cycle. Okay. Now you should be able to appreciate why natural frequency, omega n, actually represents the natural frequency. Okay, so it actually represents the number of times, right, the mass moves up and down. Okay, number of cycles the mass takes for 1 second. Okay, that is the expression for natural frequency. Okay, now a little consideration will also help us. That is, suppose you have a spring mass system. So there you can see a spring mass system. And let us say that there is a motor that is connected here, okay, with an eccentric mass, of course. Okay, this is the mass, and this is a motor that is spinning. Okay, now when this motor is spinning, now when this rotation of the motor, RPM, okay, when the RPM of the motor matches with this natural frequency in cycles per second. Okay, natural frequency in cycles per second. Natural frequency in cycles per second is given by 1 by 2 pi into root of k by m. Of course, you want to convert this into cycles per minute, you multiply by 60. Okay, so that will be natural frequency in cycles per minute. Okay, so the natural frequency and the forcing frequency of the motor, because it has an eccentric mass and it is rotating at a certain RPM, and every time this eccentric mass is rotating, it exerts a force. Okay, and it's a centrifugal force, right? M into omega squared into r, and you can see that the centrifugal force exerted radially outwards. And if you resolve the centrifugal force into two components, one force vertical and the other force horizontal, and you look at the vertical force, and if you look at the vertical force, and if you just resolve the vertical force, it will be, say for example, this is theta, the vertical force is m into omega squared into r into sine theta. Theta can this time be represented as m into omega squared and r into sine omega t. So this omega should be differentiated from the natural frequency omega. Okay, there is a suffix n. And you could see if you plot the centrifugal force, it also varies in a sinusoidal manner. When this frequency of the force, we call it as the forcing frequency, which is denoted as the RPM of the motor. And the natural frequency, which is denoted by the expression k by m, when there is a match, when the natural frequency matches with the forcing frequency, so that leads to resonance. So at one point of time, the amplitude becomes so high that it's just going to break. Okay. So this is for now. We have derived the expression for natural frequency of a simple spring mass system, which is 1 by 2 pi root of k by m. And we have also discussed the concept of resonance. So thank you all for your patience. Thank you so much.